Hey there, and welcome to this explainer. I am absolutely thrilled you're tuning in today because, well, we're going to unpack something truly foundational. Whether you're aiming to be an electrical engineer working on massive power grids, or you're just kind of curious about how the electronics sitting right there in your home actually work, there's one fundamental rule you use almost every single day. I'm talking about Ohm's law. So let's just dive right in and demystify the absolute bedrock of electrical engineering.
Now, before we even peek at that famous formula, we absolutely have to understand the three individual pieces of the puzzle. Seriously, if you get these three things down, the formula is basically going to write itself in your mind. First up is voltage, which we represent with the letter V. This is the driving force. Think of it as electrical pressure. Imagine you have this massive water tank. A higher water level creates a tremendous amount of pressure at the bottom, right? And that pressure is what physically pushes the water out through an attached pipe. In that exact same way, a higher voltage creates more electrical pressure, pushing more electrons through a wire. But here is the absolutely crucial distinction. Voltage itself doesn't actually flow. It's totally stationary. It is strictly the pushing force that makes everything else happen.
And that brings us to current, represented by the letter I. Current is the actual movement. If voltage is the pressure of the water sitting in our tank, current is the actual water flowing inside the pipe. The literal amount of water flowing past a certain point every single second, that is exactly like electric current. More moving electrons every second simply means you've got a higher current. And we measure this flow in amperes, or, just amps. Finally, we have resistance, represented by R. Resistance opposes the flow of current. So imagine that same water pipe, but now it's incredibly narrow, or maybe it's all clogged up with gunk. Even if the driving water pressure from the tank is incredibly high, only a tiny bit of water actually comes out, because the pipe itself is actively fighting the flow. In an electrical circuit, resistance makes it physically difficult for electrons to move. We measure this opposition in ohms. So, we obviously can't see electrons with the naked eye, which is exactly why electricity can sometimes feel, well, a little abstract. But by mapping this onto a physical system we can easily picture, our trusty water tank and pipe, we can perfectly visualize how these three distinct elements interact. Let's compare two scenarios side by side. On the one hand, you have high pressure combined with a wide pipe. That means a ton of water easily flows through. Translated to electricity, high voltage plus low resistance equals high current. Now, on the other hand, let's say we keep that high pressure, but we switch to a very narrow pipe. The pressure is really fighting to push water through, but the pipe is fighting back. Less water flows. So, high voltage plus high resistance equals a low current. As you can see, simply changing the pipe's width drastically alters the entire flow.
Actually, consider this for a second. What if we have a completely clear, super wide pipe, meaning very low resistance, but our water tank is basically empty? We have low pressure. Well, even with that incredibly easy path, because you just don't have enough driving voltage pushing those electrons, you're only going to get a tiny little trickle of current. It takes both the push and the pathway to dictate the final flow.
Now that we've got a solid grip on the physical reality, we can look at the math. And it is a beautifully simple, elegant equation. Voltage equals current multiplied by resistance. It represents the exact physical water pipe rules we just established, provided things like temperature stay constant. Let's see this math in action. In case 1, with our resistance locked in at 10 ohms, applying 10 volts of pressure gives us 1 amp of current. If we double the pressure from 10 up to 20 volts, boom, our current perfectly doubles to 2 amps. They are directly proportional. Now check out case 2. We lock our voltage at 20 volts. With 10 ohms of resistance, we get 2 amps of current. But if we double our resistance, making the pipe twice as narrow at 20 ohms, our current is cut exactly in half, straight down to 1 amp. Current is inversely proportional to resistance. I actually want to pause here for just a second. Why is this simple formula, V equals IR, the absolute starting point for almost every single electrical calculation in existence? Just think about that for a moment. The reason Ohm's law is so incredibly paramount is that without it, electrical engineering would literally be impossible. Engineers rely on this exact math to design safe cables, correctly rate fuses, and build everyday circuits so our homes don't, catch on fire. Let's look at a practical, everyday example. Step 1. You plug a standard space heater into a 230-volt wall supply. Inside that heater, the heating element has a resistance of 46 ohms. Well, 230 divided by 46 is 5, so the heater safely draws a steady current of 5 amps.
But now imagine step 2. A dangerous fault occurs inside the device. Maybe a wire melts and shorts out part of the heating coil, dropping the heater's resistance completely in half, down to 23 ohms. What do you think happens to our current?
10 amps. It immediately spikes to double the normal amount. So, the absolutely crucial takeaway here is this. This massive, sudden jump in current is exactly why low-resistance faults produce extremely dangerous, high currents in power systems. It is the exact reason your circuit breakers are designed to trip. They are basically doing Ohm's law in real time to keep you safe.
And by the way, it scales way up to massive infrastructure too. If you're a transformer design engineer working on the national power grid, you use this to calculate winding current, determine voltage drop, find copper losses, and estimate massive fault currents. Even though complex power grid designs often use a broader concept called impedance, that whole shebang rests directly on the humble foundation of Ohm's law.
As beautifully simple as this equation is, well, like all rules in physics, Ohm's law has its boundaries. It doesn't just work for absolutely everything in the universe. Ohm's law remains perfectly valid only when certain conditions are met. The temperature has to remain constant, the physical dimensions of the wire can't change, and the material has to be what we call an ohmic conductor, like your standard copper or aluminum. If a wire gets extremely hot, its resistance naturally changes, and that simple linear math just breaks down. And perhaps more importantly today, Ohm's law completely fails to describe the behavior of modern semiconductors. I'm talking about diodes, transistors, or those LED lights you probably have in your house right now. Those devices have a non-linear relationship between voltage and current,